least squares estimation. So I would like to talk first about some kind of the background and general solution. Then, first of all, I'll define the problem. What does it mean to solve a least square problem? And then, as we have done, like in the review of probability theory, we'll first go from the general problem to the case where the randomness is Gaussian. Over there, you will see, you can guess very nice solutions if everything is Gaussian. Discuss some properties of the estimation before we go to some examples. So the problem definition looks like this. We have a jointly distributed random vectors, x and y. And I haven't specified whether x and y are Gaussian or not. So in this case, just the random vectors can have any kind of distributions. So the goal is to find this, is to solve this minimization problem, is to find this x hat that minimizes, so you see this expectation sign, minimizes the variance between x and x hat, given some information y. Okay, I have talked about sort of the background for this kind of problem. X in the future will become the state of the system, which we want to estimate. And y is sort of the measurement we can get. We don't directly get x, but we get y. So we want to solve this. Someone told me, if I don't have y, if I don't get the measurement y, what would be a candidate to solve this minimization problem? If I don't know y. X is random. We can try the mean, right? X is random, but we can know the mean. If we know the mean, x hat, we can choose the mean as an estimate of x. In that case, what will this become? If x hat is the mean of x, the variance, right? So now you will see that if we have y, if we have some measurement y, the solution is just going to become this. The solution is going to become also a mean, but it's the conditional mean given y equals y1. Okay? So and the solution is kind of quite easy if you recall what we did in the taking the partial derivative of vector functions. Okay? So you can just so x hat is nothing but a variable that we can use different values here. So just define this function here, and we just want to find z, which is going to minimize this. So just expand this equation here. This by the way, this is a 2 norm. So whenever I don't specifically say what kind of norm it is, I meant 2 norm. 2 norm is x transpose. It's this guy, the vector transpose times the vector itself, okay? So it would be x minus z transpose x minus z, okay? Now just expand this product here. I'm going to have x transpose times x minus, so this is going to be 2z transpose. And then, yeah, I have an expectation sign here. So let me write it. So first of all, I have the expectation of x transpose times x, and then I have the expectation of z transpose. Then I'm going to have an x given x conditioned on y equals y1. The expectation sign is going to come here. So I can take, be careful here, I can take the expectation sign to be here instead of here, because z is not random. Z is the thing we can choose, all right? X is random, so the expectation is on x instead of on z here, okay? So the last term is going to be z transpose times z, and as I told you, z is deterministic, so expectation doesn't. Expectation of this guy is itself. So now, this guy, this function here, you see, is quadratic with respect to z. I have the quadratic function of z here. So just to optimize the function, I just need to solve this quadratic function minimization problem. So take the partial derivative with respect to z, let it go to 0. I can get the solution. And I want you to understand that solution is intuitive. I've explained to you why expectation is one type of estimate for x. Now, if I have the additional information, then it's just the conditional expectation given some measurement of y. Okay? So if you want to write out the full solution, you just express the expectation sign, expectation term to this full integral kind of mathematical expression here. So there's one thing that you need to be a little bit careful over here for this optimal cost. Okay, optimal cost is just plugging x hat to this function here. Then you're going to get the optimal cost. Let's say J mean. It's going to be, so plugging x minus x hat over here. So this is some kind of scalar, okay? So in the end, this thing, this whole value is going to be a scalar. It's not a matrix. So x, let's say x is a 2x2 matrix. So if you express out this 2 norm, it's going to be like this, right? So this is a scalar. So this is a 2 norm of this guy. If I denote this as a I denote this as B, A transpose, let's say. So it's a fact that A transpose times B equals trace of B transpose times A. Okay? So in this case, this is a scalar. Look at the trace here. Equals BA transpose. Equals BA transpose. I made a typo here. So B is a vector. So you see, B times A transpose is some kind of matrix, right? You can verify this result. This is in general true. So if A is a vector, B is a vector, A transpose times B equals trace of B times A transpose. You can verify, for example, A equals A1, A2, B equals B1, B2. Okay? So A transpose B equals nothing but A1, B1 plus A2, B2. Now, B times A transpose equals, as you can see, it's going to be B1 times A1, B1 times A2, and then B2, A1, B2, A2. So taking the trace of this matrix is going to be this guy plus this guy, which equals this guy. Okay? So if you want to generalize a little bit, okay, this is a fact. Trace for, if AB are matrices, so if AB are matrices, then trace A transpose B is going to be equal to trace B transpose A. Okay? And the fact behind this is that a trace is the matrix inner product. So you understand, for the vector case, A transpose B equals B transpose A. So A transpose B times A transpose times B is the vector inner product between two vectors. So for the matrix cases, trace is the inner product. Okay, so that's just extending the discussion a little bit. So let's take a look at some of the ideas coming out of this solution here. So conditional expectation minimizes this quadratic squared cost. So as you can see, the solution, I haven't specified any probability distribution for x, either for x or y. So the solution holds for any probability distributions. And you see, we have sort of talked about this idea. If I give one measurement of y, I get some conditional expectation here. If I don't give you any specific value of y, then this is a function of y. So I give you a y value, then it returns me a different value of x, expectation, conditional expectation. So x hat, you see, is a function of the random vector y. So whenever I don't specify any kind of measurement y1, then we can write this x hat as the expectation of x given y here. Now, what I will do, and in this course, what we will be following this today's lecture is for the cases where x and y are Gaussian. So I want to briefly summarize why Gaussian are important before we discuss the details of mathematics. Okay? So we we learned the central limit. We reviewed the central limit theory, which is saying if a lot of random process identically independently distributed, then the summation of them will approximate the Gaussian. So in real world, we have a lot of randomness all over the world. And then the superposition of this randomness is going to give us Gaussian. That's why Gaussian are common in practice. Okay? And the second reason is that Gaussian has very nice properties that make it mathematically feasible to solve many practical problems. So I will give you the intuitions for these points. So first of all, PDF of Gaussian is solely determined by the mean and the variance. We have learned the PDF of a Gaussian. Then this is very important. Linear functions of a Gaussian random process are still Gaussian. So if you filter a Gaussian random process through a linear system, the output is linear. It's Gaussian. Someone tell me why that's the case. Or if I ask you to prove this, what will you do? Linear functions of Gaussian. Let's suppose x is Gaussian. Then I ask you to prove ax plus b is Gaussian. A, b are scalar, constant scalars. That's true. That's very close to answering the question. Just go one step further. Yeah, that's exactly the case. So if you write down the PDF of this guy, you will see it's still going to be an exponential type of function. So we can know the mean and the variance of this guy. So from the PDF, we can still know it's Gaussian. Now, I have mentioned this. Output of an LTI system is Gaussian if the input is Gaussian. Okay? This guy we have talked about also. So if x1 and x2 are jointly Gaussian, then the conditional distribution are Gaussian. This is the result we did the mathematic evaluation of the PDF in 2 lectures ahead. Okay? Lastly is this one. If two jointly Gaussian distributed random variables are uncorrelated, then they are independent. So you see here, the message here is that if Gaussian and uncorrelated, then this implies independence. Okay? The converse is not true. If two random variables are independent, that doesn't mean they are uncorrelated. Not at all. But if it's Gaussian and uncorrelated, then we have independence. So this is very nice property. This can also be proved out from going through the PDF of the random vector. So we learned also whiteness of random process. So I want you to understand that Gaussian and white, they are different concepts, okay? A random process being white, what does that mean? It means xk and xj, if k and j are not equal, then k and j are uncorrelated. But you see, Gaussian is talking about something else. Gaussian is talking about how a random variable has the probability distribution. So this is talking about the probability distribution. This is talking about how the random process evolves with respect to time. So totally different concepts. We can have Gaussian random noise, which is usually the case. But it doesn't. We can also have uniform white noise or Poisson white noise. In this case, it just means if I have x1, xk, xj, the first case just means for each x1, xk, xj here, they are Gaussian. But xk and xj, they are not related because it's white. And for the Poisson case, it just means the distribution for each of them satisfies a Poisson distribution. Okay? So the whiteness is talking about something else. Okay? We talked about Gaussian white. It is used a lot because it's a good approximation for a lot of practical noises. So we have reviewed why Gaussian is important. So I'm just going to dig into the solution of the Gaussian case. Okay? So the conditional distribution, the conditional mean of x given y, if x and y are Gaussian, we have this equation, we have derived this equation before. So I mentioned I want you to sort of memorize this equation as it's so useful, and we're going to be using it again and again. So it's the expectation of x plus additional information given by y. Okay? And things will matter if x and y, they are related. Okay? So here is the cross covariance between x and y. If x and y are totally independent things, as you can guess, y, you give me y, but y is not related to x, then I won't be able to improve my estimation at all. So that's the case. That's why this term happens here. If this is 0, then I'm not improving my estimation at all. So look at the solution here. It has several nice properties. First of all, this estimation, conditional expectation, is unbiased. Okay? If you take the expectation of this guy, it's going to be equal to x. So expectation of E xy equals expectation of x. There are two things I want you to be careful about. First of all, what is this expectation taken with respect to? This outside expectation. Meaning, what's the randomness in this term here? What is random in this term? X, not quite. Y, right? So I've told you that this guy, this expectation guy, is going to be dependent on what information of y you give me, right? So the first thing, this expectation sign is given, is taken with respect to x, and then this guy is taken with respect to y, okay? So after you've taken these expectations, then we're going to get this, okay? The proof of this guy can be taken as an exercise. You just use the PDF of the two random variables. Then you can prove this fact. So the estimation is biased. It's unbiased, which is nice above all. Okay. So the second question I want to ask is, in this case, x hat. If x and y are Gaussian, is x hat Gaussian or not, and why? How many of you think it's Gaussian? So the rest of you either are not sure, probably are not sure. I think that's the case. I could have asked how many of you think it is Gaussian and how many of you think it's not Gaussian. It's colored, that's correct. But it is Gaussian. See, expectation of x, is this deterministic or random? It's a constant value, right? Also, in this case, these are just constant matrices. Constant, constant, constant. Only randomness is y. Y is Gaussian, so this is Gaussian, because it's a linear function of a Gaussian, right? So x hat is Gaussian. And as a matter of fact, because x is Gaussian and x hat is Gaussian, so no matter how you operate, as long as it's a linear operator, this guy is also Gaussian. So because it's Gaussian, we can talk about covariance of this and all the additional properties, random stochastic properties of x hat. Now, look at the covariance of x hat. So this is just the definition of covariance, okay? You can write it out. X hat, plug this guy inside here. You can write it out. And then in the end, you're going to get this guy. Covariance of x hat equals this. This is just by pure definition. Because of this, this is the most important message for this slide. If you take a look at the residual, so I want to estimate x. If you take a look at how good, if you want to evaluate how good we are estimating x, we have to take a look at the estimation error, which is defined by x minus x hat. Okay? First of all, I told you that x hat is unbiased. So if you take the expectation E of x equals expectation of E hat, so this is zero mean, which is, first of all, very nice property. Second of all, the covariance of this estimation error, okay? Covariance of this estimation error. If you evaluate, okay, this is the definition, and then this is the result. To get this, let's see how you can get this. X given minus expectation. So there are probably several ways. Let's do it once to obtain this covariance estimation. So I want to evaluate expectation x minus conditional expectation. Transpose. So we have seen that the conditional expectation equals the expectation of x plus cross covariance between x and y, and then y minus expectation of y. Okay, just plug this inside. I'm going to get x minus expectation of x minus x xy x y y inverse y minus expectation of y. Then it's transpose, its own transpose. Okay. The first term after the product with the transpose itself is going to give me expectation of x minus ex, x minus ex transpose. Then there will be another project. So the second term is going to give me expectation of x xy x y y inverse y minus mean of y. Then because of this transpose sign here, this guy itself is going to be taking the transpose, becoming transpose, and then x y y inverse x. This guy is transpose, x y transpose. Okay, so there will be another term. What's the third term? Third term here is the cross product term between these two guys in this quadratic function is going to be minus 2 expectation. Let's see, I'm going to use this guy ahead. X, x, y inverse, y minus expectation of y, x minus expectation of x. Transpose. Okay? Everyone has any problems, questions up to this step? Okay? So look at this term here. These are constant matrices. So taking expectation, the expectation is can be taken here. So these are constant, doesn't matter. So if you put this expectation sign inside here, this quantity is equivalent to x, x, y, x, y, y inverse. What's the expectation? What's the expected value of this middle term here? It's the covariance of y, x, y, y, right? And then there will be another x, y, y inverse term. So this guy got canceled. I'm going to have x, x, y transpose. But x, x, y transpose equals x, y, x. So this is the result here. And then this term, the same logic. Constant matrices won't change the expectation sign here. So I can take this inside here. I'm going to get x, x, y inverse. Then expectation of this guy, what does that equal to? It's the cross covariance between y and x. So you see, now I have one term here. I have to minus 2 of this guy here. So the result is going to be this guy. It's going to be the covariance of x itself minus this term. So that's the derivation. But the important message is this. So this guy, if you think about it, it equals mean of x. This result, because of the minus sign here, is always less than or equal to. It's not strictly less than or equal to, but this is saying the this is not the scalar less than or equal to. This is the matrix less than or equal to. So it means if I say x is like this, if x is a matrix, means x is positive definite. So that's just the notation here. This is always less than or equal to. I would say less than or equal to because it's more intuitive. Less than or equal to this guy. That means one very important message. So the error, the estimation error, if I use x hat, right? If I use this as my estimate, it's always smaller than the error if I use the mean itself. See the message? So it means taking the mean is not, taking the conditional mean is a better estimate than taking the mean itself. It means we are improving the estimation here. So by this additional term here, we are getting better result. That's the message here. Under what condition will we not be able to improve the estimation here? Right. If this guy is 0, that's the only case we won't be able to improve the result. Okay, so that's the key message here. Now, if you get that, then there are several additional properties, but these will be all very intuitive if you got the main message in the last slide here. First of all, the estimation error. We'll be always considering how the estimation error is going to be has what kind of properties if we analyze these squares. First of all, the estimation error is going to be uncorrelated with y. And then because it's Gaussian, so this also means we can easily replace it as independent. only for the case of Gaussian. If it's not Gaussian, we cannot easily replace these two. So this is saying something very nice. So the arrow, it's sort of like we have tried our best to use y to improve our result. Because you see, the arrow doesn't contain any information of y. All the information of y we have been used for the to do the estimation here. Okay, so that's first of all a good result. And then second of all, the estimation arrow and the estimate the estimate itself, they are orthogonal. So orthogonal in this case means the expectation of the inner product of the two matrices, the two vectors are 0. So if we don't have the expectation sign, and if these vectors are deterministic, that's the orthogonal in the deterministic case. In the stochastic case, we just have the expectation sign here. Okay? So I will give you the intuition of these two results by a picture, which hopefully you find it more intuitive. So I will use this one. So I will show the picture first, and then I will talk about the derivation. So it sort of like look like this. This is if we put the random vectors in a random vector space, then I have vex x. So this is a 2D case. I have the random vector x, and I have the random vector y. Okay. Keep in mind that we have measurement of y. We don't have direct measurement of x. So we can only estimate x using information of y. That's why the x hat vector is going to be aligned with this y vector. Okay, this is the idea of using information of y to estimate x. Now, what will be the best estimate of x if x hat is constrained to be on this line? Is this thing, right? I just if this angle is 90 degrees, then I'm getting the best estimate because my arrow you see, is definitely better than this. Just do a couple of examples, then you will see. My arrow is definitely going to be larger if the x hat is like this, right? So this is, you can easily convince yourself this is the minimum estimation error I can achieve. And in that case, you see, x tilde, first of all, is orthogonal to x hat. It's uncorrelated with here. X tilde is uncorrelated with y. And also, x tilde and x hat, they are orthogonal. So that's a picture for the property 1. Okay? And the derivations are actually pretty not difficult at all. So I think I'll just prove the first property. I'll just prove this guy. And then you can prove the second property very easily. So just use definitions. All these proofs are just using simple definitions. So if I want to show this guy is uncorrelated with y, I just check the cross covariance between this guy and y. So I'm actually skipping one step here, which is this. So uncorrelated, more rigorously, I should have said this. I should have written this guy first. Okay, this is actually evaluating the cross covariance between x tilde and y. Why does this equal to this? Right, because this guy is 0. Okay, because this estimate x hat is unbiased. So keep this result in mind, that the mean of the estimation error is 0. Keep this in mind. We'll be using this. Okay, so just to write out what x hat equals to. X tilde equals x minus x hat. Okay, x hat, as you have seen, is the conditional mean of x given y. Now, look at this term. This term, after multiplied by this term, is going to give me the cross covariance between x and y. And this term, after multiplied by this term, It's going to give me, again, I can take these out of the expectation sign. These are constant matrices. So I'm just going to get the cross covariance, the covariance between covariance of y. Okay, so look at the result here. The inverse, the cross covariance of y is multiplied by its own inverse. So this guy is going to become 0. Okay, so not difficult to prove, but this is the picture I want you to keep in mind. Yes. Which one? You mean these two? These two are different. In the end, I want you to obtain this one. But this is a necessary step to get this, to prove this second step. Picture. Here. In this case, it's harder to explain in this picture. But if you write out the definition of these two, you will immediately get the difference. Right. If they are orthogonal, they are uncorrelated, yes. Let's see. The other case, the other direction is still true. No, these two properties, they are not equivalent. So first of all, this guy, the first property is talking about how the estimation error is related to y. And the second one is talking about how estimation error is related to x hat. You see the difference? Right? So they're talking about two things. Okay, so that's the first case. That's the first case. If we just have x and y, if you think about it, I just have the estimation error. I just have to consider the estimation of x conditioned on y. Now, think about the situation. What will happen if I can have two measurements, y and z? Y and z will both give me information of x. Okay, so let's take how the situation, how the is going to become. So the full statement is like this: if y, z are Gaussian, if for the simplified case, if they are independent or uncorrelated in the Gaussian case, then we can still estimate x. All right. So imagine, convince yourself that the estimation of x is going to be something that looks like this. So it's again the conditional expectation of x given. Now you have y and z, two information that's related to x. So the result contains three terms in the first case. So it's the mean of x plus the improvement given me y plus the improvement if you give me z. So two improvement from y and z. And then if you notice, this expectation sign is going to cancel with this term here. Then I'm going to get a conditional mean of x given y plus this second improvement. So this is also intuitive to understand. We have seen that if I just have y, this is the best result. This is the optimal estimate I should use. Now, if I have another information of z, then just put it in here. Okay? And one more thing. You notice here, this term doesn't contain y at all. All right? This is because y and z, they are uncorrelated. So z, the information given from z, it's not going to be dependent on y at all. Okay? Alternative, now I'm going to introduce some notations that we'll be using in common filter. So alternatively, if I use another set of notations, we'll get a different result, but they're equivalent. So I'm going to introduce x hat, then slash y, defined as the conditional expectation of x given y. And then I'm going to define x tilde as the estimation error of x given y. So it's going to be x minus x hat of y. Is this result here? Okay. I'm going to also, let's see, introduce. So this will be used later. I'm going to also introduce x, the cross covariance of x tilde given x tilde as the cross covariance between x tilde, not cross covariance, the covariance of x tilde minus mx tilde transpose. So that's, again, because this is unbiased estimation, so these are zeros. I'm going to also introduce x tilde z as the cross covariance between x tilde and z. So this time, I won't write down the expectation sign because it's unbiased. Okay? This will be useful for our discussions. So, after we introduce the first, we can simplify the expression a little bit. So we can write this guy as x hat slash y. We can write this guy. We can write this guy as expectation. This requires a little bit derivation here, so let me be careful. This term is equal to this term. Okay, so let me show you the proof of this guy. Okay, let me show you why this is equal to this. So because expectation of x given z minus expectation of z equals expectation of, so x equals x hat given y plus x tilde given y. So this is immediately using the notations I just introduced. Minus. Right? We have introduced this. X tilde slash y is x minus x hat. So x, if I swap the orders, x is going to be equal to these two guys here. Now, this term equals expectation of x hat given y given z plus expectation of x tilde given y given z minus expectation of z. Okay? So can someone tell me why these two, they're going to cancel each other? Huh? Yes. Then? A little bit difficult, right? Because there's a typo in the notes. So because of this, because of the typo in the notes, this is not expectation of z, it's expectation of x from here to here. See, none of you found out this typo. right? It's because of this. This is the expectation of x. Then use the statement you just said, because y and z, they are uncorrelated. Okay? In the future, if anyone finds a typo during the lecture, he will automatically get an A in one of the homework problems. But you have to say it during the lecture. It doesn't count if you come to me after the lecture. Okay, so that's why I'll update the slides after today's lecture to correct this typo. Okay. For the estimation error covariance, okay, this is always the thing we will do. We'll first evaluate the mean, and then we will evaluate the estimation error covariance. Okay, the result. I will show you the result first. The result is it equals to. We can look at the left-hand side first. You have seen the first term, the first two terms, is the estimation error covariance if I just have y. Now, if I have another measurement, z, then it's going to be this guy minus the information given me by z. Okay? Again, there's no y here because y and z they are uncorrelated. Then this guy equals this guy here. This guy equals to this guy here. And the reason, look at this, the intuition, not reason. The intuition behind this is that this x tilde, as you see, is x tilde conditioned on y. So this is the information, this is the residual information. Notice the tilde here. This is the residual information after I have used the y. Now, this is the additional information if I have z. Okay? This is additional information. Let's see. The picture is here. I want you to understand the pictures it's more intuitive in this case. So the two statements restated are like this. The picture, you see, the expectation of the best estimate of x given both y and z. In this case, y and z, they are uncorrelated, so they are orthogonal. Given both of them, it's this guy. It's the expectation of x given y, so it's this guy, plus the second guy here is this guy. Okay? So, yeah, let me explain. So this guy, you already know why this guy happens. And then this is the residual after I have used information of y. Now, I have a second measurement z, which can provide me information of x along this direction, right? Now, if I would just do a projection of this guy onto this direction here, which is the expectation of this conditioned on z. Then sum them up in the end. And I can directly sum up and because they are orthogonal. There's no cross-correlation, cross-covariance terms in between these two. So that's, first of all, the mean, optimal estimate of mean. And then look at the estimation error covariance. It's going to be this minus, so the covariance, the estimation error covariance of this guy minus the additional information provided by this z direction. So it's going to be this. Again, this is from the. It's probably better to write out the first information. If I just have y, then if you recall your notes, it's going to look like this, x. If I just have y. Now, regard this x tilde as x here, and this z as y here. You see, z is here, y is improving x. Here, z is improving x tilde. So just the structure looks exactly the same. Just change the notations. Okay? So anyone has any questions for this picture? Yes? Yes. In this picture, yes. But think about x can be three-dimensional. In that case, it's not exact. Mm. It's is slightly the idea expressed. Your idea is correct. So if everything are deterministic, if everything are perfect vectors, then this holds obviously. The only thing is I regard this as an intuition picture. It's not the exact picture because x and y, they are random vectors. But if it's random, we can not perfectly know the value. We can best estimate it if it's random. Yeah. The real case is y and z are usually not uncorrelated. They have correlations. And that's exactly the property 3 I'm going to discuss. If y and z they are uncorrelated, what will happen? Okay? So that's a very important question. If y and z, this is exactly the case here. If y and z they are correlated, meaning they are not orthogonal, what will happen? How do we do that? The result, this is the result. It's going to look like this. So I'm going to hide all this information first. If I want to estimate x given y and z, I can first of all do this. I can first ignore z. I just estimate x given y. This is the first step. So I'm going to have x hat given y and x tilde given y. Then in the second step, I'm going to start to use the information of z. But notice, z can be decomposed into two vectors, either along this one or along this one. The vector, the decomposition here will not give me additional information because this guy is exactly on the same line as y. Right? The important thing is this guy. This will give me the additional information on another degree of freedom. So this guy will give me the information. How do I do that? I just do a projection of this estimation arrow onto this line here. So which is going to be the expectation of, look at the notation here. Yeah, I have to explain the notation here first. So z can be decomposed as z hat given y, which is here, plus z tilde, this is the arrow term, z tilde slash y. And then if I want to do a projection of this guy onto this line, it's just going to be the expected value of this condition on this information here. So the final answer, as you can see, is going to be the best estimate of x given y for the case y and z are correlated. It's going to be x hat given y plus this guy here. Expected value of x tilde given y conditioned on z tilde given y. This is the most common case. This is the most practical case. Okay, so it's written here. The equation is written here. Any questions for this part? Okay, then if you look at the second covariance matrix, is exactly in the structure of this. Is exactly similar to this guy. XY. So this is improving, y is improving x here. Here, this z term, this z tilde term is improving my estimation conditioned on y here. Just a change, just a different notations here. The structure is exactly the same. Okay, so this is a pretty important, as you can see, this is a pretty important equation, how the estimation error behaves look like. And then this picture is an important picture. How are we estimating x using different values of, using different measurements of something that's related to x. So these will directly give us a very, very important idea. So this is now we're using that in a control system. In a control system, we have input to the control system, and we also have noise. Suppose the system states are xk. This is the state of the system. We can only measure y. So we have mentioned this at the beginning of last lecture. It's very important to estimate x of k, given all the previous information y0 to yk. So this is a very important problem. And think about what we have done. The tools we have been using is this. Now we'll be able to estimate x given yz. Okay, we can very easily extend. It's going to be very easy to extend this to minimal measurement. Let's say OPQ. It's going to be the structure is going to be derivation is going to be exactly the same. So this is going to directly give us tools to do this step. I will use maybe around 10 minutes to do one example. Here we'll be using all the results we have learned today. So it's a sensing problem. Suppose we have a motor that's rotating. The speed, the velocity of x, the velocity of the motor is x, and there are, because of the gears imperfections of the rotations, there will be some randomness inside. So suppose x has the following stochastic properties: mean 10 radian per second and has a variance of 2 radian square per second square. We have two sensors. This case is a relatively easier case. So the two sensors both measure x, but with additional noise inside. Suppose V1 and V2, let's see. Okay, yeah, suppose V1 and V2, they are, I'm assuming V1 and V2 are uncorrelated. Suppose let's see whether this is the case. Let's assume for now V1 and V2, they are uncorrelated. Okay, they have zero mean and they have sensor noise inside. Okay, so let me ask several questions. Look at the first one here. Are x and y1 related or not? The answer should be pretty obvious. They should be uncorrelated. They should be related because I'm measuring x using y. If they are not related, then I'm not doing estimation at all. So what about y1 and y2? Are they related or not? Because both of them contains information of x. Okay. What about v1 and x? In this case, no, because v1 is a noise. It's a sensor noise. So yeah, it's here. They are uncorrelated. v1, v2, let's say independent of x. Okay, so suppose I just have one measurement. I just have one sensor. Let's see, how will I be best estimating y1? Best estimate of x given y1. X hat y1. If x and y1 are both Gaussian. So I'm going to need to use this equation here. It's going to be the mean of x plus x y1 y1 inverse, then y1 minus the mean of y1. Okay? The reason why I asked you the questions previously is to let you recognize that this x hat given y1 is a random vector. It's a random, in this case, random variable, because y1 is random. Okay, so to be able to obtain this, I'm going to need because y1 is random, then we're gonna need these quantities, cross covariance between x and y1, and cross covariance between covariance of y1. So these can be very easily obtained. Just follow the definition here. Cross covariance between x and y1 is defined by this quantity here. If x1 is if x has a mean of 10, what will be the mean of y1? This should also be pretty easy to obtain. It's going to be the mean of x plus v1. So someone can immediately get a in one of the homework problems. Huh? Three, two, one. There's a typo here. Huh? C? What C? No. Okay, none of you will get the bonus. Mean of y1 equals mean of x plus mean of v1. Huh? Previous page. No. Yes. Here. That is huh? Here? No. Okay, so this guy from here to here. From here to here. Actually, I lied. There's no typo. I just want you to focus. But there's one trick I did here. I swapped something. Mean of x equals mean of y1. Yeah, that is true. I skipped this step, that the mean of v1 is 0. And then I swap the orders. So y1 equals x plus v1. So I put this ahead. y1 equals x plus v1. So I swapped the order a little bit. Okay? But it's a good exercise. I want you guys to, it's good you are following the derivations here. Okay? So write it out. Then look at the result here. From now on, I wish you to be able to directly, after you see this, directly tell me the value of this guy. If I tell you the variance of x is 2, if I tell you variance of x is 2, and I tell you x and v1, they are uncorrelated, what will this guy give me? Nice. What about this case? A little bit more. Everybody see that? It's going to be the variance of x plus the variance of v1. And because v1 and x, they are uncorrelated, so there's no cross product term. So it's going to be, yeah, this is 2, this is 2. 2 plus the variance of v1, which is 1, so it's going to be 3. Okay? So do this practice yourself, because when deriving the common filters, we'll be using these tricks again and again. Okay? So now we have obtained this. We can put them here. Then you see, this is the conditional estimation given y1. The result should be quite obvious. Now you see exactly, this is the randomness comes from y1. Other terms are all constant matrices, constant values, not constant matrices in this case. Okay? So similarly, you can do the best estimate of x using only y2, which is going to be exactly the same, because not exactly the same. Replacing y1 with y2, because y1 and y2 they have exactly the same structure. So just replacing the notations, you're going to get it. So now, actually what we wanted to do is estimate using both y1 and y2. This is what we wanted to do. And I'm going to show you how the result is going to improve if I have two measurements. So again, if forget about what we derived from the beginning. If I just ask you this question, even if you haven't learned today's lecture, you should be able to do this. The intuitive way, straightforward way to do this is going to be the expectation of x given, now this is a y. This is a vector y, right? What should be the expression for this? So check your notes. It's going to be equal to this guy plus x, xy, xy, y inverse, y minus mean of y. So because I know how y looks like, so I can evaluate these matrices. I can have no problem getting this, 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 and this. The only difference in this case is what? Since our matrices, we have matrix operations. So we're gonna get matrices in this expression, and this is the result. Okay. So it's great for low order computations. But imagine if I'm doing experiment and I take measurement over 1 hour. I take a measurement every 1 second, and I measure 1 hour. It's going to be a huge, huge matrix here. And take the inverse of that matrix is going to be really pain. That's why we need it. That's why we learned. This approach. This approach. So we can. This is using property 3 of the least squares estimation. Is this? We can first do the estimation using only information of y1, and then after we get the second measurement y2, we improve our estimate. That's the key message here for that kind of operations. Okay, so we have done this actually, right? This is in the first question. Yeah, we have already done this. We have already finished this step, which is the best estimate of x using only y1, and we have obtained this solution here. This is the best estimate of x given only y1. Okay, so the only remaining step is to get this guy here. Okay, so I have written down the result we have obtained first. So how do we do this step? Can someone take a look and see what should be the steps? So the key thing is to recognize what is random in here. Y2. Anyone has another guess? Y2. That's a good guess. This guy is also random. The randomness in here is from V1, right? Because V1 contains noise. So to check that, you just express. Can everyone see this? Okay, so the estimation error of x given y1 is going to be x minus the conditional expectation of x given y1, right? And then if you write it out, this is going to look like this. And this V1 comes from y1. This is the measurement noise in y1. Okay? So it is true for someone answered this correctly. So this guy is going to contain randomness from y1 from y2. So that's the result here. Okay? To obtain this, how do we obtain how do we obtain y2 tilde slash y1? It's the conditional, the definition is like y2 minus y2 hat given y1. And this is a conditional expectation. So I'm asking how do we obtain this guy? What it is? What is that formula? Exactly. So just apply this equation here, the conditional mean equation here. So I can know expected value of y2 without problem. And then because y2 equals x plus v2, and y1 equals x plus v1, we can do the yeah, it's useful. Let's do one of them. We can do the cross covariance between y2 and y1. It's going to be equal to expected value of y2, which is x plus v2 minus the expected value of y2, which is going to be expected value of x, because v2 is the zero mean. Then the second is going to be x plus v1 minus mx. So I won't need a transpose because we are doing scalars here. Now, look at this guy. Can someone immediately tell me what this value equal to? It's again using the trick we discussed earlier. Y, but there's no y here. That can also work. But what about if I just give you this? I just want to use information of x. You see? Exactly. So it's x minus mx, just a shift it here. Then I'm going to have a square term of this guy. So it's going to be the variance of x plus, then I'm going to have the cross product term between v2, v1, and v2 x minus mx. But because of the assumptions that v1, v2, they are independent and independent from x. So the result is this. So similarly, let's do one more exercise. What about x, y1, y1? What does this guy equal to? X plus v1 minus mx, and then its own transpose. No, there's no transpose because it's a scalar case. What does this guy equal to? Excellent. Right? So all of them can be very easily expressed. Just use the definition of the trick we have been using. So then I'm going to get this guy. This guy. So we have explained how to get this. If you write everything out, it's going to look like this. Then just follow the notations. One more step to do. So now we have known this guy and this guy. What is the conditional expectation? What's the final result going to look like? Again, use the conditional mean equation. This guy is going to be equal to x tilde conditioned on y1 plus cross covariance between x tilde y1 and then y2 tilde y1. Y2 tilde y1. Everyone sees this? Inverse. Then y2 tilde y1 minus the mean of this. Let's say y2 tilde y1. Okay, just use this equation to obtain this guy, final result. So this some algebra, but in the end, it's going to be look like here. This is a useful result here. You see, now I'm using both information from y1 and y2 to estimate in this estimate of x. I think that's the last slide. Okay, so again, the reason why we're doing this example is that in practice, this will usually be the preferred way. We can improve our estimation step by step. Okay, so as a review, summary, what we have done is, first of all, we started with this big picture. So this works for any random distribution of x and y. The minimizer for this least square problem is going to be the conditional expectation. And then we moved from there to the Gaussian case. And we explained why Gaussian are important. And we arrived at this central equation, this equation, the conditional mean equation. Then we discussed different cases. If I just have one measurement, what will be the result look like? If I have two independent measurements, what will it look like? And if I have two correlated measurements, how the results will look like. Okay? On Thursday, we're going to start using these facts in a common filter. Okay? So unless there are questions, you're free to go now.